All right, so here we have a parallel circuit. Now we know that this circuit is a parallel circuit because the two resistors are in parallel. Now if you remember, in a series circuit, the current flows exactly the same throughout the entire circuit. So nothing changes regarding the current, but it is the voltage that's divided. Hence why a series circuit is also called a voltage divider. Well, it's the opposite within a parallel circuit. So within a parallel circuit, so parallel circuit, it is the current that's actually divided while the voltage remains the same. So as the current goes here, it's met with this node here, which separates the two resistors, meaning the current has two directions it can flow. So that's why the current gets divided and goes to both resistors. Now, this is why this circuit in particular is also called a current divider. Current divider. Now, we want to actually find out how much current is being divided through, this node and then out to this node. So through I1 and I2. The way we can do that is through Ohm's law, and Ohm's law refers to V equals current times resistance. So we can apply the same thing and actually find out what I1 and I2 are specifically. We can rewrite this equation as I is equal to V divided by resistance. But this is the total current here. This is the total current in a circuit, and we only care about current 1 and then current 2 individually. But we can apply the same exact equation to actually find them individually as well. So I1 in this case is going to equal to still the same voltage source. So there's not going to be a V1 or a V2, again, because in a parallel circuit, the voltage always remains the same. So there's going to be an even amount or the same amount of voltage going through R1 as R2. So that's why V remains the same. But the resistance that we're focusing on is going to be R1 because R1 is what current 1 is flowing through. So this would be the equation for current 1. And same thing for current 2. So current 2 is going to be equal to the same voltage source divided by R2, because this time it's going through resistance 2. So if we actually, this is actually a very simple problem. We can just plug in the values that we've been given up here and solve for each one. So if I say I1 is equal to, I have a voltage source of 12 volts divided by, and I have 3 ohms for my resistor 1. So that'll be 3 ohms. So this will equal to 4 amps. So the current going through resistor 1 is going to be 4 amps. So current 1 is 4 amps. And then let's see what current 2 is. So current 2 is going to equal to still 12 volts over, and then what is the resistance of resistor 2? It's going to be 6 ohms. So it'll be 12 divided by 6 ohms. And this will equal to 2 amps. So the current going through resistor 2, aka current 2, is going to be 2 amps. Now, how do we actually check if what we wrote down is correct? Well, we can apply KCL's law to find out whether or not what we did is correct. KCL states that the equivalence resistance, that means the total resistance within a circuit, has to equal to all the other currents added up, equaling to the equivalent current. So I equivalent has to equal to current 1 plus current 2. So the current 1 and current 2 have to add up to the equivalent current. So how do we actually find the equivalent current? Well, we know that equivalent current can be represented like this. This is the same as the total current equaling voltage divided by the total resistance. So that is important. So let's actually rewrite KCL, this equation, into V over R form. So we can say that V divided by R equivalent is equal to, and we know the equation for the other two, it's going to be V divided by R1, V divided by R1 plus V divided by R2. Now, we don't know what the equivalent resistance is, so now we have to find the equivalent resistance. Well, if I factor out the voltage from here and here, I can divide the voltage from both sides, and the voltages all cancel out. So then I'm left with 1 over R equivalent is equal to 1 over R1 plus 1 over R2. And here we can just plug in the numbers to find out what R equivalent is. So R equivalent is equal to, the value of R1 was 3 ohms, so we have over 3 ohms. The value of R2 was 6 ohms, so we have 6 ohms. So if we do some basic algebra here, we can see the common denominator being 6 ohms. So we can multiply this fraction by 2. So 2 times 2 times. So then this will equal to 3 over 6 ohms. 3 over 6 ohms. But this is not the equivalent resistance. This is the 1 over equivalent resistance. So we have to actually rewrite this as R equivalent is going to equal to 3 over 6 is 1/2 to the negative first power ohms. Now, the reciprocal of 1/2 is 2, so that means that the R equivalent is going to equal to 2 ohms. So now that we have the equivalent resistance within the circuit, we can actually come back up here to this first equation to find out what the current equivalent is. So if we rewrite this down here, we can say that current equivalent is going to equal to the voltage source divided by R equivalent, which is equal to 12 volts divided by 2 ohms. So this will all equal to 6 amps. So the total current within the circuit is 6 amps. So current at the beginning has to be 6 amps. And then as it goes through, when it gets divided, when you add what's divided together, it has to equal to 6 amps, which we defined it here with KCL. So if we actually confirm what we got for our I1 and I2, which was 4 amps and 2 amps, we can see that 4 plus 2 amps is in fact equal to 6 amps. And therefore, what we found for current 1 and current 2 matches Kirchhoff's current law. Therefore, it's correct. So we can also simulate the circuit in CircuitLab to test whether or not our findings is true. So if I go to the Simulate tab and I see what goes through current 1 and goes through current 2, and I run the simulator, I can see that the voltage throughout both resistors is actually 12 volts. So it remains the same as the voltage source, and current 1 has 4 amps and current 2 has 2 amps, confirming the behavior of parallel circuits where current gets divided but the voltage source remains the same.